Hello, everyone. My name is Xiao Guangrong, and I'm working for Intel. Actually, this topic is contributed by Li Liang and Yunhong, but due to some reasons, they cannot get here. So I'm doing the presentation instead of them. This topic is about real-time and fast line migration update for networking function visualization. As we know, real-time is the key performance for NFV, and line migration can be used to balance the workload between multiple computer nodes, and also it can be used to do faster recovery and some error conditions. In this topic, we will talk about some hardware features which used to improve the performance of real-time. Also, the hardware features to speed up line migration. Last, we will introduce the software development we recently did in the community to improve real-time and line migration. Intel innovates some features to make the visualization be friendly to real-time. In this presentation, we will introduce cache QoS, epic visualization, and posted interrupt, and VMX preemption timer. One of the features of cache QoS is support to monitor the cache usage for the shared cache. Shared cache means the cache is shared between all CPUs. Also, it can support to monitor the total and the local bandwidth for the shared cache. Generally speaking, local bandwidth means the communication between CPU socket usually is a NUMA system, and the total bandwidth means all the memory bandwidth. Linux Proof tool has support this feature, so we can directly get the proof tool from the source code of Linux kernel and use it to monitor the usage and the bandwidth of the cache for the specified application. Another feature of cache QoS is support cache allocation. As we know, the shared cache can be used by all the CPUs. So all the CPU used it complete fairly. So we can check this case that the low priority application can use lots of caches. That makes the cache is not enough for the high priority application. So this is not good for the real-time because the real-time workload has high latency of the memory access. With cache allocation technology, we can limit the cache is used by low priority applications that make sure the memory access is fast enough for the real-time workload. So cache allocation can specify the amount of cache space that application can fill into. Each application can associate it with the COS. COS is the value can be set to the MSR of the CPU. this picture is from the Intel software developer manual. The first case is the default case. So that is also the case if CIT is not supported. In this case, these 4 applications can use all of the cache. The second case, the first application, COS0, can use all of the cache. However, the second application, COS1, can only use some subset cache of the COS0. Similarly, COS2 only can use subset cache resource of COS1. The cache resource of COS3 is the subset of COS2. The third case is that each application has the portion of the cache, so there is no cache contention between this application at all. Cache QoS also support to separate code and data. From this picture, we can see we can specify the cache resource for the code and for the data separately. So this is the performance data for the CIT. We can see from the picture if we didn't use CIT, the worst case is between 12 and 24. After we use the CIT, the worst case is only between 6 and 9. The second feature I will introduce is the epic visualization and posted interrupt. Actually, this feature has been mentioned many times in this KVM forum. This feature can directly inject the interrupt to VM. The interruption includes the local interrupt. For example, the API between CPUs, and also include the external interrupt. For example, the interrupt is generated by the PCI device, and the PCI device is passed through to the VM. So this feature can avoid VM exit. This picture shows the performance of posted interrupt. We can see after enable posted interrupt, the interrupt latency can be reduced a lot. This feature is about VMX preemption timer. The traditional timer has some disadvantage. For example, if the VM wanted to set up a timer, it first needs to configure the virtual timer device in the VM. That will cause VM exit, then KVM and QEMU get control. The hypervisor needs to emulate this virtual timer device. Then it call HR timers to set up the timer for the virtual timer device, and the HR timer needs to configure the physical timer device. So the physical timer device can generate timer IRQ. The timer callback can signal the vCPU thread. After the vCPU thread is running, then the timer IRQ can inject to the VM. CI has a very long path. VM preemption timer is much different with the traditional timer. There has a counter in the VMX VMCS. The timer is done if the CPU running in the VMX no root mode. When the counter reaches 0, the CPU will be switched back to the VMX root mode. Then the CPU thread can inject the timer to the VM. There is no thread context switch, and it can reduce VM exit because only one VM exit is needed. More important, we can skip the HR timer subsystem. We can skip the hardware timer device the interrupt. Now let's look at the software enhancement we recently did to improve the real-time performance. Recently, we are working on non-threaded VFR MSI. In the real-time kernel, the kernel will use threaded LQ handler on default. However, this is not good for KVM. For example, if the vCPU thread is running, then the LQ generate interrupt in the LQ context. We need to schedule to the kernel thread to handle this LQ. Then the kernel thread signal the vCPU thread. Then we need to wait. Then we need to schedule the vCPU thread back. Then vCPU thread is able to inject the LQ to the guest. So the vCPU thread is scheduled out, and the kernel thread is scheduled in. Then vCPU thread is scheduled in. Then generate LQ. They are match thread context switch. So if we use non-threaded LQ, things can be changed like this. vCPU thread running, LQ generate hardware generate interrupt. The LQ handler in the interrupt context can signal the vCPU. Then after finish the LQ handler, the vCPU thread can switch back. Then it can is enabled to inject the LQ to the guest. This is the performance data after use non-threaded VFR MSI. We can see the interrupt latency also can be hugely reduced. Now let's look at the software enhancement for the navigation. Recently, we did this work and pushed it in the community. This work is that we can skip the transmission of guest-free pages. Generally speaking, we can get free page information from the guest kernel and skip them during the migration. This picture shows how does it work. Before our solution, we need to transfer all of the data memory to the destination. After using our solution, we can see the free page in the guest can be skipped. We only need to transfer for new pages to the destination. In order to implement this feature, first we should start the dirty page logging. Then we send the request to the guest kernel by using with our Bonon device. Once the guest kernel receives this request, it will work the free page list and construct a free page bitmap. Then the guest kernel can pass this bitmap back to hypervisor, also by using with our belong device. After QEMU receives this bitmap, it can skip the free page in the guest. It works, but we should pay attention on the horse because the bitmap got from the kernel contain the horse. For example, there has a MMO region on the top of 32 bits. So QEMU before transform the memory to the destination, it should skip this kind of MMO region. This is our test result. Let's see the first case. The first case is that the VM which has 8 GB RAM, and this VM just booted. It didn't do nothing. It didn't do anything. So most of memory in this guest are not dirtied and also freed. The second case is that the guest also has 8 GB memory, but we first run an application which writes most of the RAM, and then terminate this application. And in this case, lots of the memory are dirty, but most memory are free. We can see the result that the time of live migration can be reduced a lot. This is the normal case that we use the DPDK L2 forwarding to do the performance test during live migration, and we use the 64 bytes packet to do the benchmark. We can see the total time of live migration is reduced. QIT is the hardware feature to speed up live migration. QIT means Intel's Quick Assistant technology. QIT has been integrated to the chipset that can prove compression and decompression, encryption and de-encryption service. QIT has high throughput. It can handle multiple pages in a single request. It also can buffer multiple requests. That means we can send many requests to the QIT device without waiting for completion. We should pay attention that QIT is using a physical address, so the memory cannot be changed during QIT's work. In order to integrate QIT into QEMU, all the jobs can be done in migration thread, and QEMU can send multiple requests to the QIT device, and also QEMU needn't pay attention on the zero device because QIT hardware can handle zero page perfectly. Because QIT is working on the physical device, so the user space need a translator is a virtual address to the physical address. We can use this proc file to get the information to do the address translation. Also, the memory cannot be changed during QIT's work, so mlock is needed. This is the test result for if we use QIT. The workload is that the guest continuously generate category corpus data. This kind of data is used to benchmark the performance of a compression. We can see from the result that the total level migration time can be reduced 40%. The downtime can be reduced 70%. Also, the networking traffic can be reduced 45%. Also, we can release 10% of CPU resource. This case is the worst case for QIT because the guest generate completely random data to the in the memory. So this kind of memory is not very friendly to QIT. Even under this case, QIT also can work. It can get better performance. So I have finished the presentation. Do you have any question?
So you mentioned you get the freed guest pages from the guest OS using a VirtIO device. Which device are you using?
Well, use VirtIO Gnome device.
Are you upstreaming those changes?
Yeah, we need to change the code of upstream.
Okay.
You mentioned that the pages can't be changed whilst the QAT device is compressing them. Does that mean the guest can't be writing to those pages?
Sorry, pardon?
You said that when the pages are being transmitted with the QAT acceleration, you have to mlock them, and you said they can't be changed. What happens if the guest is writing to those pages whilst they're being processed by QAT?
That is a good question. I think the memory is not directly used by QAT. It should copy. Yeah.
Okay.
So if no question, I have finished my presentation. Thank you.